this set of notes, we're going to look at continuous random variables. Previously, we looked at discrete random variables, but many random variables of interest, if measured with perfect accuracy, would result in uncountable infinite number of points upon an interval. And so a random variable which takes on any value in an interval is a continuous random variable. So let's look at two different examples that would be considered continuous random variables. Consider the random variable y equals the amount of soda a participant drinks from a newly opened 24-ounce bottle. So notice here the lowest amount that could be drank is 0, and the largest is 24. And really, if we had a way to measure, we could have any value in between 0 and 24, including 0 and including 24. So that amount of soda that the participant drinks, it could be on that interval from 0 to 24. Another one to look at is the random variable y equals the age of a randomly selected living adult participant. Well, we know the lowest age that an adult can be 18, and the person could be equal to 18. And here we're not considering age measured to the whole number. Let's say that we were going to have age, and for whatever reason we were going to measure it all the way down to a nanosecond. Now, as far as the upper limit of age, this is a little bit harder. We could look at the oldest person of living record, or we might want to allow for the person that breaks that record. So in this case, we might want to put it up to infinity, recognizing that we're not going to have a person that lives to infinity, but since we can't really put an upper bound, because we could always have a person that lives just a little bit longer than the current record holder, we could take that interval to infinity, recognizing that majority of the values taken are going to be on the lower end of that interval. For a discrete random variable, we assign probabilities to all possible points. We cannot do this for a continuous random variable because the sum of all the probabilities would be greater than 1. And this is because there are uncountably many points. And we're going to talk more about this in a little bit. But first, we're going to define what's called the cumulative distribution function, or they're just known as distribution functions. So let y be any random variable, and so this could be discrete or continuous. Then the CDF of y, denoted with a capital F. Here in a little bit we're going to see some other notation that uses the lowercase f, so the distinction between upper and lowercase is important here, is as follows. So capital F of lowercase y, that's going to be equal to the probability that the random variable y, so that's why we have the uppercase letter there, is less than or equal to little y. And this is for little y anywhere from negative infinity all the way up to infinity. So whenever we define our CDFs, we need to make sure we define it in such a way that lowercase y can be from negative infinity up to infinity. And that might sound kind of odd for the discrete case, but we're going to look at an example to illustrate what this would look like. CDFs are very useful and important since we're often interested in what are called tail probabilities. So usually when you have found a p-value, for example, you're really looking at a tail probability. And then the CDF can be calculated for both continuous and discrete random variables. So we're going to start out by looking at a discrete example, and we're going to find what the CDF is. And we actually saw this example in the previous note set. So in a study of military personnel, participants were asked to complete surveys that ask about health behaviors and health status. Participants were asked to rate their health on a continuum from poor, y equals 1, up to excellent, y equals 5. And here we have the discrete probability distribution. So let's start out by finding the CDF for this example. So remember that the CDF is equal to the probability that our random variable is less than or equal to y. So let's first start out by evaluating the CDF at these 5 different points, 1, 2, 3, 4, and 5. So notice that f of 1 is equal to the probability that our random variable is less than or equal to 1. Well, in this case, if the random variable takes the value 1, and it takes the value 1 with probability 0.008, notice that is the only value that's less than or equal to 1 that our random variable takes with positive probability. So this is just going to be equal to 0.008. Then we can find f of 2. and that is the probability that our capital value y is less than or equal to 2. Well, looking at our probability distribution, notice this is equal to the probability that the capital value y equals 1 plus the probability that the random variable y is equal to 2. And so this is going to be equal to 0.124. And we could continue in this fashion for the values 3, 4, and 5. And I'll let you verify these values on your own. Okay. So one thing to notice, as we increase y in this case, we do see that the CDF, the values, are increasing. And this is because as we move forward, or as we move up, we are accumulating more probability. So you get the cumulative probability distribution here. Now, remember that the CDF needs to be defined for lowercase y from negative infinity to infinity. So for example, we need to be able to define it for values like 1.5. Now notice that 1.5 isn't one of the values in our discrete probability distribution, but we can still define the CDF for this value. This is equal to the probability that y is less than or equal to 1.5. And since we have a discrete random variable, notice that this is equal to the probability that y is equal to 1. Because that is the only value that y takes with positive probability that is less than or equal to 1.5. And we could do something similar for any value that we want to. So for example, f at 3.33. This would be equal to the probability that the random variable y is equal to 1, plus the probability the random variable is equal to 2, plus the probability the random variable is equal to 3. And we would get this probability. So keeping this in mind, we can define the CDF as follows. The CDF is equal to 0 for any y strictly less than 1. It's equal to 0.008 for any y greater than or equal to 1 but strictly less than 2. We have 0.124 for y strictly greater than or equal to 2 and strictly less than 3. And then continuing, we have 0.554 for y greater than or equal to 3 but strictly less than 4. And continuing on. So let's look at a graph and see what this looks like. So we're going to start by drawing our axes. On the x-axis, we're going to have the different values that y can take. On the y-axis, we're going to have our CDF. So notice we know by the properties of CDFs that CDF is going to have the lowest possible value at 0, and we can't have probabilities greater than 1. So I'm going to take my y-axis all the way up to 1, and then we'll do that in increments of 0.1. Okay. And then here along the y-axis, since we have this discrete random variable, it took the values 1, 2, 3, 4, and 5. That is what I'm going to place down here along my y-axis. We could go up just a little bit higher. Alright, so notice that looking at our CDF, or our function up above, that our CDF takes the value 0 for any y strictly less than 1. For y greater than or equal to 1, but strictly less than 2, we have the probability 0.008. So it's a little hard to draw here, but that is really right down here. And then for y greater than or equal to 2, but strictly less than 3. For y greater than or equal to 3, but strictly less than 4. 5, we're about right here. And again, this is a rough drawing. For y greater than or equal to 4, but strictly less than 5, about right here. And then anything for 5 or greater, we are at 1. So notice here that our CDF is non-decreasing. And it ends up, this is going to be a property of all CDFs. And again, it's because it's a cumulative probability distribution. We keep on adding probabilities on, so that function is always going to be non-decreasing, whether it's for a continuous or a discrete random variable. So we've got some properties here. It ends up that distribution functions for discrete random variables are always step functions, just like in the example we saw. And this is because the cumulative distribution function increases only at the finite or countable number of points with positive probabilities. So if we go back up to our plot, remember that we only had 5 points that had positive probability, and those were our 5 points that were defined in our discrete probability distribution. So if we look at our CDF, we see that the increases only occur at those 5 points where we had positive probability. And so we have some properties here. The limit as y approaches negative infinity will always be 0, and the limit as y approaches positive infinity will be equal to 1. F of y is going to be a non-decreasing function of y, and we're going to see what that looks like here in just a moment. And so our definition says let y be a random variable with distribution function f of y. Y is said to be a continuous random variable if its distribution function f of y is a continuous function for y between negative infinity and infinity. So here is another definition of what it means to be a continuous random variable. And for a continuous random variable, the probability that y is equal to 0. And the reason for this is, or what this tells us, is that there is no area at a single point. So let's look at what a graph could look like for a continuous random variable CDF. So along the y-axis, we're going to have our CDF, and along the x-axis, we'll have the potential values of y. On the y-axis, here will be 0, and here will be 1. And so remember, the limit as f of y the limit as y approaches infinity, f of y will approach 1, and as y approaches negative infinity, f of y will approach 0. So we're never going to cross the 1 or the 0 line with our CDF. Now down here along the x-axis, let's consider two different potential values of y. We're going to have y1 and y2, and notice that y2 is greater than or equal to y1. So, since this is going to be a non-decreasing function, what that tells us is that the CDF evaluated at y2 will be larger than the CDF evaluated at y1. So that's going to bring us to probability distributions for a continuous random variable. So let f of y be the distribution function for a continuous random variable y, then little f of y is given by the following. Little f of y is going to be equal to the derivative of the CDF with respect to y. And so wherever the derivative exists, this is called the probability density function, or PDF, for a random variable y. So going in the reverse direction, it ends up that the CDF is going to be equal to the integral from negative infinity up to y of the PDF. And we're going to look at a picture of why this is true. The probability density function is a theoretical model for the frequency distribution of a population of measurements, and note the keyword here is model. So recall that the integral gives us the area under the curve. So here we have an example of a PDF and its corresponding CDF. So if down here on the x-axis, let's say we went out to negative infinity, and let's say we went up to some a. Well, the area from negative infinity to a, that area corresponds to probability. So if we had the probability that our random variable y was less than some a, and in this picture they use a capital X, it makes no difference, remember, if we use x or y to denote our random variable. So the probability that y being less than a, that would be the integral of this function from negative infinity up to a placeholder a. And so that's exactly what we're seeing right here. So comparing the two, notice here in this portion of the curve, if I move from left to right, I'm not gathering area very fast. And so that's why you see here the curvature of my CDF. I'm not gaining a whole lot here. Once I get into this portion of the curve, notice that I'm gaining area at a much faster rate, and so we see that reflected here in the CDF. And then once I come back to here, I start to decrease the amount of area that I'm adding on as I move from left to right, and so here we start to even off again. So that's the correspondence between the two, and again, we could either integrate to move from the PDF to the CDF, or we could take the derivative to move from the CDF to the PDF. Notice since the CDF is a non-decreasing function, then f of y, lowercase f of y, is equal to the derivative of the CDF, and that is always going to be positive. So PDFs will always be above the x-axis, well, on or above the x-axis. And since the CDF evaluated at positive infinity is equal to 1, then the integral of the PDF from negative infinity to infinity is equal to 1. And this is a very important fact, because what this tells us is the area under the curve is equal to 1. So in your intro stats course, I'm sure you worked with a normal distribution, and when working with a normal distribution, you learned that the area under the curve is equal to 1. Well, this gives you the reason why the area under that curve is equal to 1, and it ends up for any PDF, in order for it to be a valid PDF, that is going to be true. All right, so we have some more properties here. And these properties come directly from what we just saw. So let's look at an example to see how we can start with the CDF and then get to the PDF. All right. So in this example, we are given a CDF, and again, we're going to find the PDF. So remember that our PDF is equal to the derivative of our CDF with respect to y. So here we have that f of y is equal to the derivative of the CDF with respect to y. So, looking at our CDF, notice that the derivative of 0 is 0 and the derivative of 1 with respect to y is 0. So what this tells us is that the derivative of the CDF is equal to 0 for any y less than 0 or y greater than 1. So looking at the middle piece now, the derivative of y cubed with respect to y is equal to 3y squared. And so the PDF is going to be equal to 3y squared for y between 0 and 1, including 0 and 1. So let's look at a graph of the two of these. So we're going to start out by graphing our CDF, and then we're going to graph the PDF. In both cases, along the x-axis, I'm going to have y. For the plot on the left, along the y-axis, I'm going to have the CDF, and on the left, I'm going to have the PDF. So we'll start out with the CDF here. We know, since this is a CDF, we know that if we know where 1 is, our CDF cannot cross that line. It also cannot go below 0. So if we look up here at our CDF, notice the CDF is equal to 0 for y strictly less than 0. We also know for y between 0 and 1, our CDF is going to be equal to y cubed. Well, 0 cubed is 0, and 1 cubed is 1. And then we have the function y cubed between the 2 points, which is something like this. And then for y greater than 1, our CDF is equal to 1. So here's a plot of our CDF. Next, let's plot our PDF. So notice the PDF is equal to 0 for y less than 0, and the PDF is equal to 0 for y greater than 1. When y is equal to 0, the PDF is equal to 3y squared, which is just 0. And when y is equal to 1, our PDF is equal to 3 times y squared. And then something like this for all the values in between. So we can see that the plots of the CDF and the PDF do look different, but notice in terms of our PDF, if we think of our PDF in terms of the area under the curve, which is what we use the PDF for, notice here we are slowly gathering area. We keep on going up, we gather more area, and then once we hit 1, we drop back down to 0 and we're not gathering any more area. And we can see that here by the curvature. Between 0 and 1, we're gathering area. So here we're not talking about the area under the curve, we're actually talking about the slope here of the CDF. And then we reach 1 once we get past y equals 1, because there's no more area to gather from the CDF. Here's another example. So for this example, we have the PDF, but we're going to find the CDF. So the first thing I want to do is I want to take a look at the PDF. And so here's a plot of the PDF. Notice along the x-axis we have y, and along the y-axis we have the values of the PDF. Also, if we look here at the conditions on our PDF, we see that the PDF is 0 when y is not between -1 and 1. And so we see that reflected here and here in our graph. So when finding the CDF, what we're going to do is we're going to break this down into 3 cases. The first case is going to be here. The second case is going to occur in this middle region. And the third case is going to appear here. All right, so for case 1. For case 1, we're going to consider y less than or equal to -1. And remember what the CDF is doing. The CDF is talking about, the cumulative probability that we are collecting for y, in this case, anywhere below or equal to -1. Well, looking at our PDF, we can see that our PDF is 0 here. We have no probability in this region, so it shouldn't be any surprise that our CDF is going to end up being 0 in this region. So looking here, we know that our CDF is equal to the integral, and we're going to integrate from -infinity up to y, which is just going to be a placeholder. And so what we're saying here is this y could fall anywhere in the region from -1 or lower. And we are going to integrate our CDF. But in this region, our CDF is equal to 0. And so in this region, our CDF is just equal to 0. Now case 2. Case 2, we're going to consider y's that are between -1 and 1. So we're in this region here. In order to find the CDF evaluated for any y within this region, we are still going to start out by integrating from negative infinity up to y. But remember that our y in this case is in that second region, so we could break that down into negative infinity up to negative 1, plus the integral from negative 1 to y, f of t dt. And again, that's because for this case, we know our y is somewhere here in the middle region, so we can break our interval into those two different pieces. So our first integral here is going to be 0 plus the integral from negative 1 to y, 3/4, 1 minus y squared, 1 minus t squared. We're using t as our dummy variable. So here our integral is going to become and then you'll want to confirm that this simplifies to the following. So this gives us the value of our CDF when y is between negative 1 and 1. And then we have one last case. And that is for y greater than 1. But again, if we go to our PDF, so looking at our PDF here, notice what happens. Once we get to case 3, we're not adding on any more probability. In other words, there's no more area under the curve. So we have added up all of the area to that point, which we know is 1 because the total area under the curve is equal to 1. So I claim that once we get to case 3, we should find that our CDF is equal to 1. And so let's see if that is the case. So again, our CDF is going to be equal to the following. We're going to break this down into the 3 different cases. And I'd like you to confirm on your own that the first and the second term are going to be 0, and that the middle term integrates to 1, so this just becomes 1. So we can write out our CDF. And it's going to be equal to the following. And you can double check there that f of y is continuous. If we evaluate this middle portion at negative 1 and 1, we will find that this is continuous. Alright, so we have another theorem here. If the random variable y has density function f of y and a is strictly less than b, then the probability that y falls in the interval from a to b is equal to the integral of the PDF evaluated from a to b. And if we think of, again, in terms of when we look at our PDF, if we think of the area under the curve, if I have an A and I have a B, if I integrate from A to B, that's going to give me the area between these two. And so that area is the probability. So here we have the exact same PDF that we had in the previous problem. So let's use this PDF to help us find some probabilities. So here we want the probability that y is between 0 and 1/2. And this is going to be equal to the integral from 0 to 1/2 of the PDF. And the integration here is very similar to what we did before. So I'd like you to solve that and confirm that you should find this is equal to 11 divided by 32. And so that is that probability. Now there's another way that we could have solved this. So the other solution is we could have actually used our CDF that we just found to help us as well. Notice that the probability that y is between 0 and 1/2 is equal to the probability that y is less than 1/2 minus the probability that y is less than 0, which is equal to the probability that y is less than or equal to 1/2 minus the probability that y is less than or equal to 0. So why is that true? That's because, remember, for a continuous random variable, the probability of being equal to a single value is 0. So for continuous random variables, it doesn't actually matter if we use the less than or the less than or equal to sign, or greater than equal to signs. And so notice this is equal to the CDF evaluated at 0.5 minus the CDF evaluated at 0. So if you evaluate the CDF that we just found at 1/2 and subtract off the CDF evaluated at 0, you should also find that that is equal to 11 divided by 32. And then in part B it says find the probability that y is greater than 0 or y is less than or equal to 1/2. Well, based on what we just said, we know that this is equal to the probability that y is greater than 0 and less than 0.5, which we just saw in part A. So again, for a continuous random variable, the equality sign it doesn't actually matter because we know the probability at a single point is equal to 0. Now this is not true for a discrete random variable, because at a discrete random variable we do have probability mass at single points. Okay, so here we have find the value of c such that the probability y is less than or equal to c is equal to 1/2. So in other words, what this is saying is we know that the CDF evaluated at some constant c is equal to 0.5. So let's see if we can find that. So we want the probability that y is less than or equal to c, and we know that this is equal to the integral from -∞ to c f of y dy. Well, we can break that integral into two pieces. We're going to go from -∞ to -1 f of y dy plus -1 to c f of y dy. So why would we break it into these two different pieces? Well, again, let's go back up and look at our PDF. We know that less than -1, our PDF is 0, and then greater than -1 but less than 1, we have this function right here. So for that reason, we break our interval into two different pieces. We have the piece from -∞ up to -1 that we know is going to be equal to 0, so that's not actually adding on any probability or any area there. So really what we're concerned with is the second piece here. So we know that the integral from -1 to c, 3/4, 1 minus y squared dy, and here I'm using y as the dummy variable. We could have used t like we did before. It doesn't actually make a difference. And this is a similar integral to what we did before. So you should find that this is equal to 3/4 c minus c cubed over 3 plus 2/3, so confirm that you can find that. And then we know that this probability is equal to 1/2. So now what we're going to do is set that probability equal to 1/2, and we're going to solve for c. And again, I'm going to let you try that on your own. If you have any trouble with that, let me know. And what you're going to find here is that c squared is equal to 3. So, sorry, let me back that up. You should find that c has one of 3 options. So c can be equal to 0, and then you'll find out that c squared is equal to 3 once you get rid of one of the c's. So this tells us that c could also be plus or minus the square root of 3. So we've got to figure out which c it is that has 50% of the area below it. And so to find this, we're actually going to go back up to our PDF and see which one looks reasonable. Now keep in mind that the square root of 3 is equal to 1.73. So looking back at our picture of our PDF, we know, sorry, let's go all the way back up here. So here's our picture of our PDF. So we want to find the point that has 50% of the area below it. So we could consider negative 1.73. So if we were at negative 1.73, that is somewhere right in here. That obviously does not have half of the area below it. It has 0 area below it. And we could look at positive 1.73, which is here, and that obviously doesn't have half the area below it. It has all of the area below it. So our third option was 0, and looking at our picture, that makes sense. 0 has half of the area below it. So our solution here for this problem is c is equal to 0 is the constant that we are looking for. And so this idea of finding the 50th percentile, or in this case we actually just found the median of that distribution, we can let y denote any random variable such that, and if p is somewhere between 0 and 1, the pth quantile of y is the smallest value such that the probability that y less than or equal to that value is equal to the CDF, which is greater than or equal to p. And if y is continuous, then we actually have this piece right here. So the median is the value such that the CDF at that constant or at that value is greater than or equal to 1/2. And so we just found the median of that previous example. Now the last thing we need to talk about is the expected value for a continuous random variable. So we've talked about the expected value of a discrete random variable before, and we saw that that was pretty much a weighted average. And so now we're going to do something similar, but we have to account for the fact that we now have a continuous random variable. So here is our definition of the expected value of a continuous random variable. So instead of taking the sum like we did with the discrete, we're now going to integrate from negative infinity to infinity, but we're still going to look at y times now the PDF, and we're going to look at this integration. So again, we're working with that same example we had before. And remember, you can look back on the previous page, but our PDF looks something like the following. So just looking at this, if we had to guess where the expected value was or where the mean of this distribution is, probably a pretty natural guess would be right at 0. Notice that this distribution is symmetric about 0. We just saw that the median was there, and so we're going to see what happens, but it would make intuitive sense here to say, hey, that expected value is probably 0. And so let's see if that is the case. So using our definition of expected value, we have the following. Now, Our definition tells us to integrate from negative infinity up to infinity, but remember for this particular PDF we only have positive area between -1 and 1, so as we saw with those previous examples, we really are only concerned with this integral from -1 to 1. And we're going to integrate y times the PDF. And again, we've worked with this example several times, so we've pretty much have already done this integral. And if you continue to work that, you should find that that is 0. So again, for this example, our expected value is equal to 0. And if you have any trouble with that integration, let me know, but very similar to the previous problems that we looked at. Alright, similar to when we worked with discrete random variables, we might be interested in the expected value of a function of that random variable, and you'll see that its definition is very similar to when we worked with discrete random variables. It's just we're going to integrate instead of using summations. And then we have these theorems right here, again, very similar to what we saw when we worked with discrete random variables. You know, we can see that the expected value of a constant is equal to a constant. If we have the expected value of a constant times a function of our random variable, that is going to be equal to the constant times the expected value of the function of that random variable, and so on. And so here to define our variance of our continuous random variable, we have the following. And again, notice this is very similar to what we did with discrete random variables. We're just now integrating instead of summing over the entire sample space. And we have some useful facts just like we did previously when we worked with discrete random variables. And so the very last thing we're going to do here is for that example that we've been working on, let's find the variance for that random variable. So here our variance is equal to the expected value of y squared minus the expected value of y squared. Notice we already found this piece, so the only other piece we need is this one. So here, the expected value of y squared, using our definition of expected value that we had earlier, we can take the integral from make this look a little better, from -1 to 1. But now, since we want the expected value of y squared, we have y squared times the PDF. And again, the reason that I'm integrating from -1 to 1 instead of negative infinity to infinity is because for this particular PDF, we know that that PDF has 0 area less than -1 and greater than 1. So very similar to what we did before. The math is very, very similar. So again, I'm going to let you check this on your own, but you should find that this integral becomes 1/5. So then to find our variance, we have the variance of y is equal to 1/5 minus 0 squared, and that was because our expected value. And so the variance is equal to 1/5 for this example. Now for this note set, I did gloss over some of the integration. If you have any trouble with that at all, please let me know. I'm happy to write those steps out for you fully and to go over them with you if you'd like me to. And so this is going to conclude this note set.